Now let's look at some examples, some generic examples of one-dimensional flow in the field scale. And when I say examples, I'm not going to talk about numerical examples here, but conceptual examples. One of them is Artesian pressure. It is when you have an aquifer bound by an impermeable layer. So this is permeable. This is impermeable or less permeable. Actually, I'm going to write less permeable. And another aquifer, permeable. And inside these, if you have different levels of water or different water heads, then if you go ahead and drill a hole into the lower aquifer, what you'll end up with is you'll end up water squirting out because it's under pressure. So this is known as an artesian well, but forget about the well now, forget about water squirting out. Now consider what's going on here. What's going on here is you have very permeable layers and a much less permeable layer. So what you have there is very similar to this original definition of 1D flow. You have very permeable place which is connected to a water reservoir, which is a water level. So there is no head loss happening in this very permeable pipe and water body. Here as well, there is no head loss happening at these speeds. There is no head loss happening in this water pipe and water body. That was why he said head at A and head at A prime are equal here, because everywhere in this water body has the same head. And all of the head loss is happening in this soil, in this permeable medium, where you have resistance to flow. So here my Akitard is not impermeable, it's simply less permeable. So, and when we say less, remember we are talking in the order of thousands or millions of times difference. So what you end up having happen is you have a high head, a low head, and a layer through which head is being lost. So you are going to have water flow like this. And while that water flows, it is going to be losing head. So then what you generally end up with is you have your total stresses, which are, as usual, some sort of weight of everything above, slope of slope equal to unit weight of total bulk unit weight of soil. Then when you plot the pore pressures, let's say you have your upper aquifers water level here, you might have something like this in there. But then for the lower aquifer, maybe you have it up here. It doesn't have to be in the air, but it's more fun when it is. So it will be in equilibrium with this particular water level. And then what's happening in between is flow. So here, up here, you have this much head. At the bottom, you have this much head, a much higher head. So there's flow in between. So there's a hydraulic gradient in between. And because it's a 1D flow problem, things are happening, things are changing linearly in between those. And if you consider the effective stresses, then what you can end up with is you can end up with something like this. If your water pressure is even bigger than the total stress, you can even go to a negative value there. You can have something like this, for example. So once again, this means you have boiling or quick condition, which we have discussed in one of the previous videos. We said when it happens if you have too much upward flow. So again, your the slope of your effective stress plot here will be the submerged unit weight minus I times gamma water. This is the slope of this is the submerged unit weight minus I times gamma water is going to be the slope. And boiling can occur here. So here, if boiling occurs even in a homogeneous soil, boiling can occur if your effective stress is less than 0 in calculation. By the way, some books also define a factor of safety against boiling and defines in terms of hydraulic gradient. But I don't like doing that because it changes depending on what you have above on top of the layer. So I'm not going to do that here. And you can also have cases like this. By the way, quick condition, like if it is clay, quick clay, if it is sand, quick sand, those terms come from this as well. You can also have this kind of problems if you are digging an excavation under the groundwater level. So you want to dig an excavation, and let's say you are going to do this. What you need, you cannot dig inside the water. You have to put your machinery and workers in here. So what you will need is, and let's have another layer down here. So what you need is, you need to bring the water level down here. But let's say this is more permeable. This more permeable layer still has this much pressure in it. So let's say this is, your water table is like this here now. But for the more permeable layer below, it still has this much head. So here as well, you will end up with flow upwards. So in a case like this, for example, you have only one type of soil, then you have to make sure for this soil to have a safe excavation base that is free of what's called base heave, which is again the same thing. Boiling, quick condition, base heave, they're all the same thing. If effective stress becomes less than 0, which means total stress becomes less than pore pressure at the bottom. So but it also will mean I upwards is going to be greater than or equal to gamma prime or gamma submerged over gamma water, where gamma submerged is simply submerged inflate, because your effective stress is increasing by this much, and the head due to elevation is changing this much. So if you do the math, it's going to come down to this, and this is called the critical hydraulic gradient. So a factor of safety against boiling is defined then as I critical, which is your capacity, over the thing that makes the instability, which is I upwards. So if you see something like this in the books, this is what it is. But bottom line is, keep your effective stress positive and things will be fine.